let's begin. Well then, how many degrees are in a circle? Now, if you are clairvoyant, you know which is my next question. What's my next question? Why? Of course. What does it mean? It's fine, right? But what does it mean? It's also like why. So tell me please why. Any ideas? I might imagine we have, right? We have mentioned it before, but people have very short memories. So this is the situation, guys. So the circle is sliced into 360 equal slices. And 360 degrees just means 360 Babylonian slices. Now, what's the purpose of measuring? What's the purpose of degrees? They measure what? And be, of course, as simple as you can. So sharpness, wonderful, you remember. The measurement of sharpness. How sharp is this blade, right? And I will resist quoting something. I did, it was so, I just took a breath. I felt like saying something beautiful, but then I thought, no, I suppressed it. It's like hiccups, you know. So we measure sharpness. And the more degrees, the sharper it is. But do you see, guys, that degrees are not natural? What's not natural about it is like it's not natural for me to measure my index finger with centimeters, or even less natural to measure it with inches, correct? So my finger might be maybe 2.5 inches long. Oh, here is Elazar. What do you know? He came. Maybe we should shut off all the cameras and scream surprise, right? Something like that. See if you'll get scared. Where is he? Ah, good, Sophia. Thank you for letting me know. Elazar, you are dark, my young brother. Achi Atzair Elazar. Good that you came. So back to this thing. Sorry for the yes. Oh, good. Good. Yeah, everybody's here. So, guys, 360 is an arbitrary number, just like saying that my index is measuring, let's say, 2 inches or 4 centimeters. It's arbitrary because my finger tells you there is nothing intrinsic about my finger that relates it to measurement of centimeters. But guys, if I say that my finger is as long as my nose, that's an intrinsic property. It's a relationship of, you know, it's a relationship of parts of my body to other parts of my body. You understand? It's a natural relationship. Okay, to say that the length of your ears must be the same as the length of your nose in that proportion when you draw portraits. That's a sort of natural proportion. Whereas to say that my ear is I don't know, 3 inches or 4 inches long, that's right. That's not important. That's kind of not as natural. So similarly, slicing the circle into 360 parts is not natural. Right? Somebody else might decide to slice the circle into different parts. As if, for example, the American degrees, I call them American degrees, is what? The circle measures 8 American degrees. You understand why, guys? Because the circle, the pi, is sliced into 8 slices. right? So there is nothing special about circle being 360. It's just we use Babylonian measurement. Now, Babylonians were found of base 60 systems. Now, we are using base 10 systems. What is a base 10 system? It's nothing other than expansion of a polynomial where x is 10 and where the coefficients are less than 10 and more or equal to 0. Make sense? So guys, what is, for example, if I ask you what is 153 base 10, that just means 1 times 10 squared plus 5 times 10 to the 1 plus 3 times 10 to the 0. That means that we package items first solitary, then once we have a batch of 10, we package it together. Next time we have 10 batches of 10, we package it into one package of 10 squared, etc. Do you understand? That's base 10. That's how we report numbers. We report them in bundles. We report them in groups. It's easier to count them by groups. Now, if I were to ask what is 153 base 9? Base 9 means that I'm bundling in powers of 9. It means that I have one bundle of 9 square items, 5 bundles of 9 items, and 3 separate units. If you convert this number, you get 129 in base 10. If I were to measure 153 in base 6, that would be 1 times 6 squared plus 5 times 6 to the power of 1 plus 3 times 6 to the power of 0. It will be 69 base 10. What is the 69? It means I rearrange the bundles in terms of bundles of 10. So the situation where I have grouping of 1 bundle of 6 squared items, 5 bundles of 6 items each, and 3 solitary units. If I rearrange them in powers of 10, I will have 6 bundles of 10 and 9 solitary bundles involving 1 unit in each. Do you understand, guys? What is base? Base 10 is very obvious. Base 6, base 10, base 2, very easy idea. It's just how do you order sticks, units. You can imagine ordering soldiers in groups, in cohorts, or ordering matches if you prefer, whatever you consider singletons, just the way you package them up to make it more convenient to report the count. Good. It's basically the way you tidy up and report it. So for instance, if I take 360 in base 10, I can convert it to base 60. It's 6 bundles of 60. So each bundle has 60 items, 0 bundles and plus 0 bundles of units. So basically 360 base 10 happens to be 60 base 60. You understand what 60 means? It means 60 means 6 bundles of 60 to the power of 1, 0 solitary bundles. Good. If I had something like 61 base 60, that means 6 bundles of 60 in each bundle and 1 solitary item. Good. So that's how Babylonians did it. Now for Babylonians, we have the way we measure time. So 1 hour is 60 minutes and 1 minute is 60 seconds. And that's Babylonian time. Good. Now, again, the degrees they measure, as we mentioned already, they measure the sharpness or angles. And we have the pizza cut into 360 parts. So here we see 3 slices, 3 Babylonian slices make this angle less sharp than 2 Babylonian slices. You agree? So we can see how we quantify sharpness. Now, this way of quantifying sharpness is not natural. Now, a natural way to do that, and that involves looking at the circle. If you look at parts of the circle, you see that the circumference of the circle is 2 pi r, 2 pi times the length of the radius. What does that mean, guys? This is what it means. Look at it, guys. Here I drew two circles, one circle of radius 1 inch, another circle of radius 2 inches. Observe what you can say about the crust, right? So the length of the crust, if you look at it, this is one radius. If I fold that one radius around the circumference, I get one radius length, two radius, three radius, etc. If I carry out, I will get that the circumference of this blue circle is roughly 6.28 radius units. Do you understand what I mean by radius? If you can take the radius and fold it around the circumference about 6.28 times. In particular, you can fold it 2 pi times, where pi is approximately 3.1415. What goes afterwards? I believe 9 to 6 or something like that. Remember the phrase. May I have a large container of coffee? You remember that phrase? You can expand pi to several digits. Good? Everyone's clear, guys? So I ignore the fact that it's inches. This is definitely a smaller circle and this is a bigger circle, and the same is true for the bigger circle. All that changes, my radius is longer. But it's still true that, that the longer radius folded along the larger circle is going to fit on the circumference about 6.28 times. For simplicity, we can say 6 times, but you think a little, you know, it's irrational. It's something else. Good? So when you say circumference is 2 pi r, it just means that if I measure the radius in inches, then the circumference is 2 pi times the length of one radius in inches. But really 2 pi r just refers to, the 2 pi is the important pi. 2 pi r is just converting the units into inches, right? Every circle is a unit circle. Do you know what I mean? If I make the radius the unit length, then every circle is a unit circle. I can imagine that when I do the circumference, I measure the circumference in terms of how many times that one radius is fitting around. Good? Do you understand what I mean by that, guys? Right? So what the numbers you impose on an object, it's just the units with which you measure it. They're kind of artificial, but the geometric part is that the radius fits 6.28 times. I hope I'm not repeating it way too much, but I'm hoping it sticks in your head. Here it is, guys. Here I took the circumference and I uncoiled it. What Veritasium does, he actually takes pizzas. You can see that he obviously got this idea from me because my notes are much older, you know. So he uncoils the pizza and lays it, the crust, lays it flat, and you can see that the flat crust is going across 6 pizzas, right? Going across roughly more than 6 radius lengths. So 3 pizzas altogether, because a pizza has 2 radius, you know. So you uncoil it and you can stretch it along the diameter of 3 pizza pies. And that's what I did here. I uncoiled the circumference and I flattened it out. Good. Now, radian measure, do you understand now, guys, that radian measure is the measurement of the crust. So when you take a wedge, a slice, you just measure how long is the crust in terms of radius units. And that will be your measurement of the angle. The longer the crust, the more obtuse is the angle. You with me? Now, if you're with me, I'm asking a very simple question. I hope it's simple. Why is radian measure natural? You understand, guys? In calculus, you don't use degrees. Degrees produce awkward results, but radian measures produce very natural results. Nice results. Why? Well, a bit more elaborate. It relates to length because it's intrinsic. Okay, that's a bit better. Numbers that are less complicated. What's complicated, not complicated, it's a bit vague. What do you mean less complicated, more complicated? You understand, guys? Mentioning that my finger is, let's say, this index finger is 2.5 inches and my nose is 2.5 inches. It's somewhat, there is an intermediary. The intermediary is not necessary. You see this? The nose and the finger are the same length. That's natural. To measure it, compare it to some properties that are outside of myself that are foreign to me, especially inches. Inches are tremendously foreign to me. Like I refuse to answer physics problems that are stated in feet or inches. I just ignore. I mean, I don't believe in that measurement. Right? Everybody knows there is a meter, they should stick to meters. Everybody knows there is a kilometer, they should use kilometers. The fact that we're using Fahrenheit and pounds is terrible. We need to change that. Yes, has to be meters, Celsius. My God, guys, what's a normal temperature, right? What's a normal body temperature? Tell me what it is in Celsius. How many of you know? 37, my God, I mean, it's so imprecise. Here we go, 36.6. My God, guys, 36.6, 37, you're kind of already sickly. You're not feeling that well most of the time. Yes. And what's the temperature when you are very bad? It's 40 degrees Celsius. And when you are dying, it's 41, 42. Has to be, once it's 40, you have to drop it. Now, converting it to American things, I have no idea. 100 something fever, I kind of refuse to learn it through all the years that I'm here. Good? All right, guys, so here is that situation. So here is the relationship between degrees and radians. Exactly. No matter anything, we know the circumference is going to be that many radii. Very good answer. You understand? There is this invariant, guys. So here is how we're measuring angles. The two ways, they're kind of displayed in this pizza slice. So you can see that this slice is supposedly 2 degrees, which means this slice is measured to be two Babylonian slices. That's right. This slice is 2 Babylonian, this wedge contains 2 Babylonian slices. Now, how many radians it contains? This is 1 radius, and I measure the circumference of the crust. You understand? I can report the radians by just measuring how long is the circumference. That's what you do when you're riding a car, guys. You know, when your car is turning, the wheels are turning, and you have odometer is updating how much distance you traveled. What you calculate is you translate the revolution of the wheel into distance traveled. And that's very easy and natural to do because the revolution of the wheel, when you revolve the wheel once, you measure the circumference of the wheel. You understand? It's like the circumference of the wheel is laid flat on the ground. Now with degrees, that's not natural. Make sense? So radians is using the length of the crust, but length of the crust as measured in radius units. Good? So when you think very simply, degrees, think the slice, radians, think about the crust. So guys, please tell me what's the relationship between degrees and radians. 1 degree corresponds to how many radians? 1 degree is how many radians? Calculate. Thank you. Well, the other way around, Alexandra, the other way around. Come on, guys, it should be knee-jerk reaction. Good. Good, Sophia. Of course, I hope it's not just memory, guys. You understand what that means. We're going to talk about it. Pi over 180. Thank you. Just breathe. Thank you so much. What about the rest of you guys? I mean, it's too obvious that you don't want to type it, I hope. Exactly. Now, how do I know that, guys? Imagine that we have 360 slices. That's how I think of it. Those are 360 twins. They are all the same. Each Babylonian slice is like another Babylonian slice, yes? And all together, all the 360 slices all together bring a combined crust of 2 pi. right? 2 pi, because that's the, if radius is, we're measuring units radius, we have 2 pi radius lengths they brought together. Do you agree? You imagine what I'm saying, guys. Each slice is bringing part of the circumference. 360 of them bring the full circumference. So that means that 2 pi divided by 360 is the contribution of one slice. You follow? Easy, right, guys? I mean, easy imagination, right? Just here is a slice. Here is what they carry, the crust they carry. Each of them carries the same amount of crust. Crust. Yes, what is it? It's 2 pi divided by 360. And which simplifies to pi divided by 180. Now, of course, I want to make a very, how do you say, embarrassing confession. When I was in school, I could not understand. I thought, didn't you say that pi is 3.14? So why are you suddenly saying that pi is 180, right? So 180 slices is the same as pi. Do you agree? So something in school, I mean, I knew if I replace pi by 180, I could easily convert to degrees and something like this. I didn't think more of that. Do you understand it, guys? You know, pi is 3.14, and then they say pi is 180. Could anybody clarify my confusion, please? Do you have the same confusion? Do you feel that same thing that I felt? Okay, good, Alexander. It's not a value for pi. So what is 180? Dauda means it's a made-up measure. One is degrees, okay. But I mean, I don't understand. Yes, one is radians, but what is that we're talking about? Is the angle. All right, so let me maybe say it in my words, okay, to clarify it, guys, right? So 1 kilometer, you know kilometers. 1 kilometer is 1,000 miles. So it's not like 1 equals to 1,000. It means that 1 kilometer carries within itself 1,000 meters. Similarly, pi radians, in other words, the angle that that has a crust of length 3.14, you know, a crust that is roughly slightly more than 3 radius in length, will carry how many slices will build it up? 180 slices, Babylonian slices, make up that crust. You understand? The amount of crust that you obtain from about 3 radius units will be equivalent to 180 slices. They need to stack them together. You understand? So it's a sort of relationship. Does it make sense, guys? So pi is not 180. It's just the amount of angle of pi radians corresponds to 180 Babylonian slices. Very easy. I hope it is easy. I don't, and of course you should not worry. At a very old age, I did not know that. I did not understand that really. I just kind of could figure out. You just replace pi by 180 and get something, but I never cared about mathematics, just like you. Good. So now, guys, it will not trouble you to please convert 2 degrees, 180 degrees, 120, 60, 90, and 45 degrees to radian measure. What is that, Elazar? Ah, okay. One over pi, careful. Pi over 90. Okay, that's for A. Guys, it should take you a few seconds, at least the idea of it. Thank you, Nicole. Ayodele, thank you. Good, good. Thank you, Alexandra. Dauda, you're telling me 3.14 is what? B. Come on, guys, faster and faster. Oh, Jeffrey joined, good. All right, let's do it together, guys. Should take you a few moments, right? So 2 degrees. What's 2 degrees? 2 degrees is 2 times 1 degree. 1 degree is pi over 180, which gives me pi over 90. I converted it to radians. Do you understand what is pi over 90, guys? It means that the amount carried by 2 degrees is the same as about 3.14 divided by 90. That's the length of a radius. Good? Which means if it's the 3 radius, 3 divided by 90, it's about 1 divided by 30. About a 30th of a radius. Good? And the rest are the same. 180, you understand how to do it. 120, 60, 90, 45. You all know how to do that, correct, guys? I don't need to speak about it. Yeah? Wonderful. Now, how do you convert degrees to radians? Now I want you to tell me what is 1 radian in degrees. 1 radian, how many degrees? Good. Very good, Moshe. Very good, Ayode. Very good, fast response. Wonderful, Avram. Wonderful. You all understand it, guys. Not by memory. You just feel it. Good. Just to be sure, guys, what's happening here? We have 2 pi radians. If you prefer, you can think of it. 2 pi radians feels like 6. Do you agree? 2 pi, just to simplify it and make it a simple number, let's pretend it's 6. So 6 radius units carry together 360 Babylonian slices. These carry this many degrees. That means that 1 radius carries, carries 360 divided by 2 pi. 2 pi is the 6 something, right? 6.28. So what did we get? We get that the one radian is approximately pi. Sorry, it's approximately 180 divided by pi. Now, what is that? It's approximately 180 divided by 3, a little bit less than that, right? So what is 180 divided by 3? So you can expect it's approximately 60 slices. You understand? One radius, so something that has a crust of 1 radius length is equivalent to slightly under 60 Babylonian slices. You understand, guys? So that the numbers make sense to you. So you understand how much pizza do you eat? How much pizza can you eat, guys? I can eat 1 full pie in one go. Can you? Here is a slightly more precise, a big one. So it's about 57.296. Good. It's about 57 something slices. Good. Reminds me now of Cool Hand Luke. He had to eat 50 eggs. Okay, guys, here is the next question. How many degrees are in this wedge, in this sector? Calculate, please. So the length is, you know, the edge of it, the side of it is 3 inches long, and the arc here is 1 inch long. So I want to know how many degrees and how many radians. Of course, you can use that if you need. Good, good, Elazar, good. But that's radians converted to degrees. Yes. <sighs> 60 over pi degrees. All right. So let's do it together. Are we ready, guys? It's very simple. So first, as many of you mentioned, we measure crust. Exactly, Moshe. We need to measure crust, but we don't want to measure it in inches. Inches are annoying to us, right? So this is 1 inch, but what is it really? If I take this quantity and divide by this measurement, I get the measurement in terms of radius. Make sense? Because this length divided by 3, each time you get 3, each 3 inches, it's 1 radius. So this arc, it's 1/3 radians. You follow? I hope you understand why you divide, guys. It's some people divide, but they don't see it. It's 1/3 of a radian. Now, what's 1/3 of a radian? You remember that 2 pi radians is 360. Good. So 1 radian is 360 by 2 pi, or 180 over pi. So I need to multiply that by 1/3, giving me 60 over pi. So it's about 60 over pi, I mean, less than 20. You agree? It's less than 20 degrees, about 20 degrees more or less. Good. I said 20, but it's really 19. Make sense? Easy, right, guys? It's all this fast, all those huge, boring books that you have there for high school. That's only because they have to push you with a stick. But now you're learning it on your own. You're excited. Now, guys, we are ready to talk about polygons and angles. Before I move on, any last questions about degrees and radians? In this class, we are not liking degrees anymore. We don't like Fahrenheit or feet or all those things. We ignore that and we move to normal measurements. We move to radian measure in calculus, right? Whereas there is some argument about what's better, Fahrenheit or Celsius. There is no argument what's better, degrees or radians. Radians are natural. Well, of course, Celsius is better. I agree with you. That's also not argument there. Yes, and somebody tells me European as you used inches. Yes, well, that's true. I did use inches, but that's only because I need to have diplomacy with the Americos, right? I need to have diplomacy with you. So what is the sum of angles of a triangle? Guys, what's the sum of the inner angles of a triangle, please? Think about it, type in the comments. I want to see, there are now 30 people, 30 answers. Okay, good. 21 answers. And of course, great. I mean, I'm assuming you all know that. Now, what's my next question? Of course it's y. Now, I actually kept it a secret. I started thinking about it rather late in life, and I thought everyone knew that. I really had the feeling that everybody knew it. I would never have admitted that I'm thinking about such things. I thought they would laugh at me. Everybody knows. Now, do you know, guys? I came up with a proof, which is not the one I'm presenting. This one is better, but I proved it for triangles then. I was very happy. Do you know the proof of it, guys? And the proof of it is very simple. Do you ever walk around a park, guys? Do you ever kind of walk in one direction around the park? Oh, here we go. Okay, so you live by Central Park, so you go around Central Park. Around it, you know, fully around it. Good, good. Now, guys, have you noticed something, right? So you walk around, and just to help you imagine, you attach this index, and you are walking around. Let's say maybe it's a triangular path, park, right? So you walk around in here. You see that part of the motion rotates you, and part of the motion keeps this pen pointing in the same direction. So look at it. I walk around this wall of the park, and then here I turn. So when I turn, I'm turning in the same direction. I walk more, and I turn. I walk more, and I turn. Yes? Now, how much have I turned in total, guys? Anybody would tell me? Once I go through all the turns that I make and get to my initial position, once I make a full circle around the not just how many times I turned, but how much have I turned? How many radians have I turned? Or if you prefer, how many degrees have I turned? That's the important question. I want you to get it. Very important. You definitely are not walking in a circular pattern, but you're walking around the spark. Look at it, guys. Do you see what happens? How much have I turned? Jeffrey, what do you mean 3? So I made 3 turns, yes, but how much have I turned? How many radians have I rotated? Or how many degrees have I rotated, whichever you prefer? Anyone? No, you don't rotate 180 degrees. And each turn is not necessarily 60. No. And see what people say there. I am facing the original direction, 360. Finally, we got it. Look at it, guys, very carefully. You have to get that principle. I am always walking in the same direction. Are you with me? Always moving in the same direction. Not zero. I mean, you don't round it out. Look at it in the same direction. I walk around. I turn. I walk more. I turn. I walk. Turn. If I'm turning in the same direction, and I ended up pointing where I pointed when the trip started, I must have made a full revolution. Do you get it? So 360. So Avram, okay, fine. Let's see.
Do you mind saying that again?
I will say it again.
Thank you.
Look at it. You see, here is where I'm pointing at. You see, here is the direction in which I'm pointing. Let's begin walking around the triangle, but it has nothing to do with the triangle. It could be any shape. Give me any shape whatsoever. If it's a closed shape and I walk around it, I must have walked 360 degrees. It must be so. Why do I know that? Because look at it. Here is my initial position. My initial position, I'm looking along this line. That's where my nose is pointing. Do you see my red pen? That's where it's pointing. Now here I make my first turn, A prime. I have no idea. Some people said 60, but you're trying to use symmetry that's not here. It has nothing to do with triangles. It has nothing to do with the shape. It's just the shape, if it's closed upon itself, then I made some turn, I call it A prime. Now, do you see that that's the first time I made a turn? Now I'm facing this way, yes? Now I make the second turn. I have no idea how much I turned, but now I'm facing this way. Now I made the last turn, look what happened, and I'm facing the same way. You understand? How do you look? Think about it. Do you see it, Abraham? Right? Imagine imagine you have the camera. You have, like, let's say, you just suspend the motion, so you walk on the air and you just keep track of the turns. Turn, right? So how much have you turned your head around? Your head must have turned 360 degrees or 2 pi radians. Do you understand that, all of you?
Yeah, because you're facing the same way that you started originally.
Exactly, and it's not zero, Safa or whoever else answered it, because for it to be zero, I have to kind of, maybe if I was turning left, I have to then turn right to cancel it. I did not cancel that turn. I twisted. If you ever suffered from a mental disorder or you're obsessive compulsive, you feel that you are attached to a string, right? And if you turn one way to the left, you would feel that to unwind that string, you have to turn one way in the other direction. If you suffered from that disease, then I want you all actually to suffer from it, because then you understand that revolution is remembered, right? If you turn in one direction once, it's 360. Turn twice, it's 360 times 2. You see, you're coiling that spring. You follow? So the answer is 360. That's your turn. 2 pi. No, zero is not the same as 360. Zero just means you did not complete any rotations. Zero makes you face the same direction, but 360 means that you coiled that spring once. If you turn in the same direction twice, you now twisted that spring. Imagine that you have a rubber band attached from your hand to the heavens, right? Or like a safety belt. Yes, you see, Safa, or I'm sorry if I or Sophia, I think whoever was speaking, Sophia, sorry, right? Sophia, imagine you have this belt, right? If you turn the belt 360 times, it's not the same as if you haven't turned the belt. Do you agree? Have you ever had this belt tangle in your car? If you know what I mean, guys. You drive, right? You've known that you can twist the belt 360 and the belt is tangled, twisted. Of course, it's not the same. Where did you all disappear? You're hiding from me now. Who disappeared? Somebody disappeared. Good. Do you see it? Good, Duad. I'm glad you are. Are you with me, guys? You see what I'm saying? So 360 is definitely not the same as zero. The reason you might think it's similar is because you're pointing in the same place, but either you're pointing with the belt twisted or you're pointing with the belt the way it used to be. Good. And here is that picture. You see, guys, I try to draw the picture. I just take this line, here it is, and I take this line. This is a parallel line, and this line. I suppressed all the motions, your motions without rotation, and that produces a circle. Good? So here is a very, very easy argument. Look at it, guys. So the inner angles are A, B, and C. I know nothing about each individual angle, but what do I know? I know that the inner angle plus outer angle is equal to pi because they lie on the same straight line segment. Do you agree? The inner angle plus outer angle is pi, or 180 degrees. I prefer pi. Well, we're talking about it, whether it is or not, Jeffrey, right? So I'm glad you're in suspense. And your question is, of course, this is the type of question that makes me worried. I also wonder if the sum of angles is 180 degrees. So here is what happens, guys. A plus A prime plus B prime plus C prime. Here it is. It's equal to 3 pi. You all see my calculation? That means the sum of all angles, inner plus outer, equals to 3 pi. I'm interested in the sum of the inner angles. Now the outer angles, they add up to 2 pi. You see, outer angles add up to 2 pi. So we have inner angles plus 2 pi is 3 pi. That means that the sum of inner angles is pi. Did you understand it? Very simple proof if you understood that the sum of outer angles is 2 pi. Good? Confirm, guys, that you understand, or ask me questions, please. So I want to see what? I want to see 30 confirmations of understanding, or some people that say, well, I don't know something here, or I'm confused by something, please. $11 answers so far, 12, 13, 14. I'm waiting. Abhishek, what is 15? Guys, I so far only received half confirmation. Half of you confirmed it. There are 30 people. The other half don't understand. Very simple. Look again. Ah, yes, yes. Thank you, Abhishek, for counting. Good. I now see. Look at it. Outer angles add up to 2 pi. Why? Because outer angles, I just keep track. When I move through the outer angles, I rotate around. I return to my original position, always rotating in the same direction. In this case, I decided to rotate counterclockwise. Good? When you view it from above, I rotate counterclockwise. So that means that the sum of A prime, B prime, and C prime is 2 pi. Good? 2 pi. Here it is. I try to show you where you see this line. Here it is. Do you see this line? Here it is. Do you see this line? Here it is. 2 pi. Now the sum of A plus A prime, B plus B prime, and C plus C prime, I don't know them individually, but they are on the same line. So they make half a circle. So they make pi radians, or 180 degrees. And so what do I get? I get that the sum of the angles is just pi radians. And now let's check that you understand it truly, guys. You're going to tell me what's the sum of the inner angles of any quadrilateral. What's the sum of the angles of the quadrilateral? The sum of the inner angles. Okay, and calculate it. Okay, 2 pi. Good. And the inner angles? What's the sum of the inner angles? Thank you, Jeffrey. Outer is 2 pi. In inner is also 2 pi. Beautiful. Beautiful. Now let's see why. Very simple, guys. You see, do you understand the principle? The outer add up to 2 pi. Outer plus inner add up each to pi. Right? This is pi, this is pi, this is pi, this is pi. So all I have to do is I see 4 of them. So there are 4 pi. The sum of them is 4 pi. And I need to remove the outer angles, which is subtract 2 pi. You understand? Sum of all of them, it's 4 angles multiplied by pi minus the outer, which is minus 2 pi, which gives me the result of 2 pi. Good. And then quickly tell me this figure. This is any polygon with 5 sides. What's the sum of inner angles, of the inner angles? Understand what I'm asking? Okay, wonderful. I see 1, 2, 3. 3 people are responding. Good, good. Good, good. Very good. So the answer is 3 pi, because look what you do. 1, 2, 3, 4, 5. 5 pi, subtract 2 pi. When you subtract 2 pi, you remove the outer angles. Do you understand? It's very quick. You agree, guys? Now, please tell me what is the sum when you have an arbitrary number of vertices. So if I gave you a polygon that had n vertices, n means, let's say, maybe I have a polygon with 1 million vertices. So n is just any number. If I had n vertices, tell me please what is the sum. Nicole, yes, you just need to put parentheses in Moshe about n minus 2, right? Because n minus 2 pi can be confusing, but I think you understood. Right? I mean, it's annoying to type it. Good. So you understand it's n minus 2 because you count n angles multiplied by pi and subtract 2 pi. So it's n minus 2 multiplied by pi. Thank you so much. Very good, guys. So one short comprehension check, very short, okay? If I were to draw this figure, guys, let's say if I were to draw this, okay? And I make you walk, this is some sort of pond, and I made you walk around it. How much will you turn? How much will you turn? Two pi, 360 degrees. You understand? You will turn once. So the number of times you will turn is 360 or 2 pi. It doesn't matter that I didn't indicate. It's because you eventually face in the same direction. Right? First time you face in the same direction, it's 2 pi. Good. Now one more short question just to see. What if I do this? Okay, and I walk, let's say, in this direction. Well, the question is, how much will you turn? All right. And the answer is, of course, 0. Because look what happens here, guys. So this shape consists of, well, careful. Maybe I'm wrong when I said 0, right? Let's see here, right? So we have this curve, and we turn minus 360 here, right? We have this curve, and this curve is if I walk like this, so this curve is 360, and we have one more curve. So maybe you actually had it right, all of you. We have this curve, which is 360. So yes, we do turn 360. Correct. This you do in complex analysis, guys. That type of thing, because you walk, you know, you need to keep track of angle. Complex analysis is pretty cool and scary. Good? Understand. This is just not important for our class, but hopefully you understand. Because you're here walking, why the minus 360 part happened. Did you all do that like this, guys? Right? The minus 360 is you change from, look at it, you change from moving, you're just keeping track of how much you turn. You turn clockwise and counterclockwise. Do you agree? When you walk along this path, you walk counterclockwise, but then in the inner angle, you walk clockwise. You understand? You imagine untangling. So you imagine that there is a string above your head, and you see how many times you twist it. So once you twist it, then once you untwist it, and then you twist it one more time. So you just ask yourself, it's 0 if the belt attached to your head as you're walking is by the end of the journey untwisted. If it's twisted counterclockwise, it's positive. If it's twisted clockwise, it's negative. Good? Now, guys, it's a very, very interesting thing, actually, that whether or not the actual sum of angles equals to pi. And one of the first people to have noticed this was Gauss. He proposed an experiment to measure whether or not the angles of a triangle actually add up to pi. Because if they do, that means that we are in flat geometry. If they do not, that means that we are, if the sum of the angles is less than pi, if the sum of the angles is less than pi, then we are in hyperbolic geometry. And if it's more than pi, then we're in spherical geometry. Okay, you don't have to worry about it, but that has to do with the entanglement of space, whether space-time is twisted or not. Okay, and they actually ran this experiment already a long time ago, and to the extent of the equipment allowed, they concluded that the space deviates very little from Euclidean, at least locally. The space is very vast. So why would that be? Of course, it's a very remarkable theorem about finding how curved is your space without being outside of that space. And this is very, very interesting, of course, very interesting if, of course, you are interested in traveling back in time. If you worry about, let's say, that you're running out of time, if you consider those things, I mean, then they bother you, right? You want to know, is it possible to travel to the future or to the past? Of course, how space is curved, that's very important for that purpose. And for many other situations. Do you want to reach a star, right? Maybe that's a useful information for you. Now we are going to talk about how to communicate the vastness of space. That's area and volume. If we have a two-dimensional space, then we can tessellate that space with unit squares. And the reason is that unit squares, they stack next to each other so very well, and it's easy to tile that space up. So you can see that this space is 3 by 2, and the area of this rectangle is therefore 6. You see what 6 means? 6 means that we have 3 boxes plus 3 boxes. In other words, we have three boxes stacked 2 stories high, which makes it 6. You're just counting it. Good. So area in general is width times height. I hope you understand this formula, guys. You of course have fractions and other things, but width times height is very useful. Good. So tell me, please, what's the formula for the area of a triangle? And of course, I hope you can justify why. One half base times height. Guys, what? Why is that 1/2 base times height? Well, very easy. Very easy, at least when it's a right triangle. Do you agree? It's width times height makes a rectangle, and we just take half of that rectangle. All right, but what do we do when we have an arbitrary triangle that's not right? So one suggestion I can give you is as follows. Do you see this? Here is an arbitrary triangle, and it has width W and height H. So what I can do is, in this case, it's obtuse. I can produce another triangle here in red. And altogether, I have one big right triangle with height H and width W plus W prime. W prime, I, by the way, do not know. And I have a small right triangle, which is here. So the area of this black region is simply the area of 1/2 W plus W prime H, the area of this full triangle, minus the area of this red triangle. Are you good? Understand, guys? So the result is still 1/2 width times height. You all see that? I just add what do you call it? I add the crotches of the right triangle. I calculate the area, and I remove that. And because I can calculate in theory the area of this red triangle here, I remove it, and I get 1/2 W times H. Are we ready? Now we are about to talk about the Pythagorean theorem. You all are familiar with it. we know that the squares of the legs, a squared plus b squared equals to the square of the hypotenuse. Do you know the proof of that? There are many, many proofs, but do you know at least one? Well, using anything. And by the way, guys, I feel like some of you have disappeared. Dorian, Enrique, Safa, Sandra, Lillian, Jasperit, Brian, Dauda, anyone. If you are available, turn on cameras. Don't play peekaboo if you can. The class is very boring when you cannot see many faces. So let's look at a very easy proof, guys. Look what you can do, guys. We can take one such triangle and make 3 additional copies. Rotate those copies by 90 degrees to form the shape. Notice A to B, B to A, A to B. You see, we understand how I do it. Just take this, this triangle, rotate it by 90 degrees, rotate it by 90 degrees, rotate it by 90 degrees, you form the shape. Are you with me? Now, C squared is the area of that inner square. Now, what do I know? I see that this small square can be obtained by calculating the area of the big square and subtracting the areas of the 4 triangles. Do you agree? So what's the area of the big square? It is simply a plus b squared, and the area of each of the triangles is 1/2 ab. So what do I have? I have that c squared is a plus b squared minus 4 times 1/2 ab. Expanding it, you get a squared plus b squared. Very easy proof. Took a few seconds. Do you agree? Do you understand it, guys? Look at it again. Make a copy of this triangle to form this shape. Now I want to know what is c squared. C squared is the area of the big square minus the 4 triangles. That's it. Yes, I understood. You are now paralyzed by the amazement that it's so simple and it didn't take any effort. Or do you need explanation? Area of this is 1/2 AB. There are 4 of them. So the combined areas of the 4 triangles is 2AB. So I have a plus b squared minus 2ab. Here it is. Gives me the area, it gives me c squared. Now that brings us to the Pythagoreans. So the Pythagoreans were famous. It's a very ancient school. They were a sort of sect. In that sect, they, I have no idea why, but they avoided beans. They were terrified. Pythagoras had some sort of phobia of beans. And the legend goes that there was once a mob. Maybe they didn't like the sect. There was once a mob and they were chasing Pythagoras. And he was running away from them, but there was a cart of beans. So he decided he'd rather die than, not decided, he kind of could not go beyond the cradle of beans, and they just were able to catch him and kill him. Okay, that's how Pythagoras apparently ended his life. Now the Pythagoreans, they had this mysterious saying. They said all is number. Now, what does all number mean to you? Does it mean anything to anyone here, guys? If I said all is number, what would you think? Okay, Alexander, anything can be described in terms of number. Anything has a number you can put to it. But what's the point of putting numbers to anything? But what's the worshipping of numbers exactly? What have they worshipped? So I'll try to explain, at least to the extent I imagine understanding it. Yeah, but that's God, that's true, Elazar, but what exactly were they trying to worship? What were they seeing? I think it's not very different from the Judaic version of at least it's going in that direction. So this is, oh, this is the extent that I think of it, guys. So you see, you look at all those questions. How tall are you? How long have you studied? How much do you weigh? How fast are you driving? Is the future determined? Is there such a thing as cause and effect? Is time travel possible? All those questions in some sense relate to that idea. Can I relate something to something else? And you begin with the simplest thing that they understood, the geometry. That's the first thing that they were able to relate. When you quantify anything, what is quantification? Quantification is a way to relate one entity to another, to compare. Quantify is to be able to compare. Good? So for instance, this. I take this stick, and the stick is about 14 centimeters plus an extra segment here. Do you see 14 centimeters plus something else? Now, what is that something else? It's 4/10 of a centimeter. You understand? What did I do? I was able to describe this amount of space in terms of a space that's familiar to me because I see it, right? It's like what you do. You say, when something is large, you usually in America compare it to football fields, because I presume that everybody understands here what is a football field. Good? Yes, and that's why I can say, oh, this place is 17 football fields long. So people think, oh, I know what's a football field, and I can see what 17 football fields is, right? So here, centimeters are very familiar. So I can describe this length in terms of centimeters. Now here is a question, guys. Can I describe any length in terms of centimeters? Can I take any length and at least in theory describe it in terms of that? Measure it. What do you think? Okay, so Alexandra says yes, and Abraham said yes, and Moshe said yes. And so if you say that, then you believe that at least geometry is number, right? What do they mean by number? Is just that you can take one segment of space and describe all of space in terms of that one segment that's familiar to you. Make sense? It's just relating one thing to another. So what they believed, and Elazar, here is what I mean, it's a sort of monotheistic belief. They believe that there is one kind of space, at least in terms of geography, and they believe that there is one type kind of thing. That's the relationship, that everything is just fits together into one kind of thing, right? So usually, what do you think? You have the god of thunder, you have the god of sea, you got the god of health, all sorts of gods for every little thing, and then you bring it all together and you say there is one god. So that's why they worship it like God in some sense. They thought this means everything can be related to anything else. That's what they meant, right? You can take one segment of space, you can relate it to another segment of space. Good. Now here we see that for the Pythagoreans, there is a machine. I think I mentioned that machine to you guys. You can take any line segment and slice it into exactly 19 parts or 27 parts or 112. It doesn't matter. Give me any number. You can take a segment and slice it precisely into equal parts. They had this geometric machine. So for instance, this is not quite 15 centimeters. You have this extra segment, and this extra segment appears to be 4/10 of a centimeter long. So that means it cut the centimeter into 10 parts and add 4 of them, and you get that length. So altogether 14.4 is the length, which is equal to 17, sorry, it's equal to 72 over 5. Do you understand, guys? 72 over 5 is the fraction. So for Pythagoreans, numbers are fractions. Now, are numbers fractions? There was a person, and I told the story way too many times, but I hope you will be able to enjoy it. Yes, I mean, the people just started yawning, right? My God, right? It's just not a story again. I haven't told it to you, I hope, unless, of course, it does seem like I tell it to the same students, but, you know. So, guys, do you know? Do you know? I used to teach, I started teaching a very elementary class, and the people, they were absolutely indifferent to what I had to say. I spoke about square roots and relations and this, and thanks to them, I was inspired with the example that I am gonna mention now. So guys, is there such a thing as root of 2, root of 5, root of 3? Is there such a thing, guys? So it's a silly question, but I just wonder what you say before I start talking. So some of you say yes. Now, what is, guys, would anybody help me? Could you tell me what is root of 2? Could you type in the comment root of 2? Just want to see what you would, what I mean, you know, that just tells me, give me a number which is root of 2. But could you actually give me that number? Right, 2 to the power of 1/2. It's just, well, 2 to the power of 1/2 is just the number whose square is 2. But can you actually give it to me? So here, Jomel, thank you. You told me it's 1.414, and Elazar gave me even a bigger thing. Is what Elazar gave me a root 2, guys? So Elazar gave me a number. Is what Elazar gave me root 2? Is what John gave me root 2? Is 1.4 root 2? So some of you said it's not. So again, you did not give me root 2, Elazar, right? And the rest of you did not give me root 2. And somebody copied and pasted something huge. Elazar, right? Some sort of, all right, it's not a square. Good, so let's see what it is, guys. So first of all, there was this guy, Hypatius of Metapontum, and he knew a dirty Pythagorean secret, which is what I'm going to reveal to you. And it's very deadly. Never tell it to anybody. He decided to not listen to it. He talked about it, he blubbered his mouth, and they drowned him in the river. So Hypatius of Metapontum was drowned in the river for either that or maybe, you know, some money disagreement, who knows. But I think it was for mathematics. So here you have a triangle. This is 1 and 1. What is, so John, did you give me root of 2? You gave me a lot of digits. Is it root of 2 what you gave? Let's verify if it's not, or it is. So you see this C? What is C, please, guys? So C is the hypotenuse. Is the hypotenuse measurable in terms of the leg? The hypotenuse is not 2, guys. The hypotenuse squared, C squared is 1 squared plus 1 squared is 2, but C itself is root of 2. C itself is root of 2. Is it measurable in terms of this length? So if it's measurable, at least according to the Pythagoreans, it's a fraction. It's m over n. You understand what I mean, guys? I cannot give you m and n because I don't know them yet. It just means that maybe it's 7 over 2. Maybe it's you know, a bigger number over some bigger number, but I do not know m and n. Now I can of course impose that m and n are in simplest terms. Like for instance, 3 over 6, I can cancel out like factors and I get 1/2. I can ensure. Yes, thank you. Alas, I actually know who is Eminem. You know, my brother's friend would blast this music without stop. So I actually do know who that is. So do you see that I can reduce them into simplest terms? In other words, if a number divides both numerator and denominator, that number must be 1. Are you with me? Yes, he is with me. I'm not sure if you are. At least his screams I can hear. All right. So what do we get here? So is there such a number m over n that exists? So we can square m over n and we get 2. By hypothesis, if square root of 2 is a number, like Pythagoreans understood numbers to be, that number is some m divided by n. It's a fraction. Square it and you get 2. Now look what happens, guys. So that means that if I multiply both sides by n squared, that 2n squared equals to m squared, which means that 2 divides m squared. This means 2 dividing m squared, which implies that 2 is dividing m. For primes, guys. Primes are such things that if they divide the square, they must, or divide any power of m, they must divide m. You can prove it with using number theory. I hope you kind of feel that that's true. Good. So 2 divides m, which means that m is equal to 2 multiplied by k. Just means that m is an even number. Okay. Now, if I square m, that's the same as 2n squared, but m squared is 2k squared, which is 4k squared. Which means once I divide, it means that n squared is 2k squared, which means 2 divides n squared, which means 2 divides n. I hope you understood what just happened here. I claimed that I reduced to simplest terms. And now I see that it means that no number other than 1 can divide numerator and denominator. But what I showed is that this assumption implies that both numerator and denominator are divisible by 2. Which means, guys, that no such fraction is possible. I cannot give you any number like that. So all the things that you typed in the comments, they're not root of 2. No matter how many digits you place, that's not a root of 2. Because those digits, if you put them together, it's a fraction, but root of 2 is not a fraction. What you typed is an imitation, you understand? Not an actual root of 2, but an imitation. If you square that number, you get a number that's very close to 2, but not actual 2. Good? Now, would anybody care whether or not there is an actual root of 2? Is there an actual root of 2 or not? Does it matter? And how can we investigate with an experiment? So the students in my class then did not care whether or not there is an actual root of 2. And of course, by the way, guys, just to use that experiment, I can use a root of 5 is not, there is no fraction that gives you root of 5. There is no fraction that gives you root of 7, and so forth. Good? There is no actual, there is no fraction that will be a root of 2, root of 5, root of 7. And so they were annoying me in that class. And so what I said, okay, what about I just pick a huge brick and drop it over your head? Now, how does it relate to root 5, for instance? You see, guys, there is a fundamental relationship between cause and effect here. Now, if I drop a brick, the brick will be moving, and I use feet just for your benefit since you're American. So the brick is in free fall and it will be moving, its position will be 16t squared. 16t squared, are you with me? So in time t, the brick will have traveled 16t squared feet in t seconds. Yes? So what I will do is I will place a brick 5 feet over your head, and it will be a big brick, huge, proportional to my irritation. And I will let it go. What will happen if I let this brick go, guys?
It will fall.
Well, obviously it will fall, but you are standing below it. Will anything happen to you?
You will get hit.
Yes, you are free from calculus forever, precisely. Well, maybe, but so you see, guys, so there are two questions, of course. One question that you are concerned with, and the other question is I'm concerned with. One question you're concerned with is, does the brick hit your head? And the question I'm concerned with is, if it does, am I liable? Now, if root of 5 is not a number, and you see, guys, if you give me an expansion of root of 5, that's an imitation. If root of 5 is not a number, then this is what happens, guys. The brick makes contact with your hand at the moment t that satisfies the equation 16t squared equal to 5. You follow? So the brick makes contact with your head as soon as 16t squared is equal to 5, which means the moment of contact of the brick with your head is simply root 5 over 4. So if root 5 does not exist, it's not an actual thing, then the brick either does not make contact with, well, the brick does not make contact with your head, which means that either nothing happens to you, or if something happens to you, it's not the result of me dropping the brick on your head. You understand? Because the brick did not actually touch you. It's just the brick was falling and just you decided to fall down if it actually happens to it. So that's nothing to do with my action of tossing the brick on your head. Do you understand? So that's why they drowned. You see, this means, by the way, guys, it does look like root of 2 would be this line segment. What is disappointing to the Pythagoreans, which is what might disappoint the people that believe in one God, is that it looks like the space on the hypotenuse is not related to the space of the legs. They are kind of different types of spaces. Just like you have, let's say, Poseidon is the god of the sea, and the god of lightning is just controlling a different power altogether. The lightning has nothing to do with the sea. That's what was troublesome to them. For a scientist, they want to unify everything together. They did it initially with religion. Do you understand? So they were troubled by that because it looks now like there is no relationship. If there is a root of 5, that root of 5 is not describable in terms of 1, in terms of the unit. You see, if you take this hypotenuse, it's not a fraction. Whatever it is not a fraction, which means that method of describing will not work. Good. So I hope you are interested in root of 5, root of 6, root of 7, whatnot. And of course, as you might imagine, since we're at it, why not learn to calculate roots? Right? Do you know what your calculator is doing? I'm not saying that's specifically what the calculator is doing, but I can produce many different algorithms for creating approximations to root 2. Good. My throat is getting tired, guys. I'm not sure if we have maybe we can take 10 minutes, maybe we can take less. Yes, I wonder if we do it today. The other thing, I'm not sure if such a thing is interesting to you, but my friend from Israel ended up on the news. I do not know if you are interested in this particular thing. I showed it to my German friend yesterday. Well, who, my friend? Well, his name is Ilya Gutman. What did he do? Well, he's a reckless person. He almost got killed. That's why they showed him over there. He survived. I can show you the video in case. Maybe I'll do it after class if somebody is interested. I'm not sure if you are. Yeah, it's not related to class. He is okay. In fact, too okay. The guy is continuing doing weird things, right? He went to bar afterwards. You know, he gets himself in trouble. So yes, so what do we do, guys? Do we want to speak about root of 2 today or later, next class? You look like you really want to know root 2, right? Later, next class. Okay, right, you're tired, right? But you're excited, you understand, you are so close, you'll be out of thin air, you will be pulling roots. You would understand how to calculate them. Next class. Okay, you need a break, right? You're not now upset that I'm stopping the class a little early. Okay, So I will stop the recording.